Time is it? Yeah, it's 1. Okay, cool. All right, so let's go ahead and get started. So welcome everybody. This is the 13th colloquium this semester here at Augusta University. And today we have the privilege of having Robert Adke with us to talk about resource-constrained programming with full dependent types. And uh, Bob is a Chancellor Fellow and lecturer at the University of Strathclyde in Glasgow in Scotland. And before that, he did his PhD and postdoc at the University of Edinburgh, and then worked on static analysis of concurrent Java programs in the field for a bit. I'm very excited about this presentation because it's very related to the research that I do on the Granule project, looking at these types of graded systems. And so he works on similar systems. And so I think it's going to be very relevant to a lot of the people here today. So thanks a lot, Bob, and I'll let you take it from there.
All right. Thank you very much, Harley. Thank you very much for inviting me. It's great to be here. I mean, I'm still where I've been for the last 9 months, 10 months now, I guess, but yeah, really sort of virtually there. So this is some work I've been doing over several years now on taking dependent types and marrying it with what's called implicit computational complexity theory. So what I'm going to talk about is a system with full dependent types. So that's the kind of dependent types you'd see in a system like Koch or Agda or Idris, and marry it with resource-constrained programming. So that's kinds of programming where you can't write arbitrary complexity functions. You can only write restricted complexity functions. So why do I want to do this? So dependent type theory is both a programming language, so we can write programs in it, and so in particular we can use something like Idris to actually write programs and compile them down to real executables and run them, and several people are trying to actually get this to be the kind of next wave of realistic programming languages will have full dependent types in them. But the real sort of reason this is kind of interesting is also that it's a proof language. So we can use the same language to reason about our programs. But can we? So we can only really reason about their extensional behavior. So what I mean by that is that we can only really reason about, so if we've got a function from A to B in our dependently typed programming language, then we can make statements about, well, if I feed in an A, then I'll get back this kind of B. So we can only really reason about the extensional behavior of those functions. Now, that's kind of misses out this huge chunk of computer science, and possibly the reason why computer science isn't just any old mathematics, is that there's the concept of computational complexity. We want to be able to reason about the complexity of our functions as well as the fact they just do something. So in most dependently typed languages at the moment, you just you can prove away extensional things about your program to your heart's content. You can prove that list append is associative and so on. But you can't prove that it's linear time in the size of the input list. And this is kind of a real problem. And what one way around this is that you embed some language in your dependently typed system. So certainly almost all dependently typed systems are strong enough to embed a language in them. So then you can start talking about a language and you give it an operational semantics and a cost model and so on. But we want to actually, if you want to use dependently typed languages as a programming language, and we want to use that same language to reason about them, then we should want to reason about the programs that we write directly in the theory, not just ones we can encode in the theory. So one thing that doesn't work is having some kind of predicate for complexity or some way of measuring internally in the theory what the time complexity is going to be. So for instance, a kind of naive thing would be, well, we have a type of functions from nat to nat, and then we have a predicate, this p time here that says this function from nat to nat is a p time function. And then maybe there's some rules about p time functions, like if you compose two p time functions, you get a p time function. But the problem is that this will then allow the theory to distinguish extensionally equivalent functions, which I don't think we really want. So there's maybe an interesting way of tackling it. So the solution I'm going to propose here is to use type systems in order to restrict the complexity of functions. And there's two ways of doing this. One is the so-called implicit computational complexity. So this is where we restrict the language in such a way that all functions are within some fixed complexity class. So for instance, we can only write polynomial time functions in our language. Another way of doing it is to be explicit. So there we are explicit about the resources being used, and the types tell us what the complexity is. So we'll see an example of this later on. So yeah, so this talk is going to be implicit and explicit typed complexity analysis for dependent type theory. So I'm going to give you sort of two systems which are implicit and one system which is explicit within dependent type theory. And the core part of this is going to be use a kind of linearly typed dependent type theory that I've worked on called quantitative type theory. And then we're going to work by adding extra bits on top of that. Now, the challenges in getting this to work are, first off, having a nice systems for implicit and explicit complexity in the first place. So if you're familiar with any of the literature on implicit computational complexity, much of it uses linear logic, as you might guess, but also church encodings to encode data types. And church encodings, in general, don't work with the kind of dependent type theory I'm interested in, so kind of intentional, so-called formal type theory. And the second part is integrating these linear systems with dependent types as well. So we want implicit and explicit computational complexity type systems that have proper data types, not church encodings. And then we want to integrate with dependent types. So first, I'm going to talk about two implicit polynomial time systems to get us going. So the requirements are that these are an extension of some typed lambda calculus. So we're allowed higher order computation. So this isn't kind of restricted versions of primitive recursion, for instance, which allow which have been studied for polynomial time. And as I said, just to hammer this home, no impredicative polymorphism. So we're interested in predicative Martin-Löf style type theory at the end. So this means proper data types, definitely no church encodings. So for now, I'm just going to forget dependent types, just have the simply typed lambda calculus. And let's see what happens if we have the simply typed lambda calculus and a natural number type with 0 and successor and an iterator construct. So this is system T. So it's simply typed lambda calculus plus the natural numbers with an iterator. And so here the type of the iterator says if we've got something to do when it's 0 and something to do in the step case, then for any natural number, we get an A out at the end. So it just iterates the step case until it gets down to 0. So if we have this, then we can quite easily get to exponential time just in one use of the iterator. So it's a little bit difficult to work out how this works, but if you step through it, you'll see that the fact that the base case is successor, but in the step case, we're actually so computing a function here. If we double this function every time, then if we plug in some number n here, this iteration will compute 2 to the n of this number we plug in here. So it's certainly not easy to see this just by staring at it, but if you work out a few steps, you can convince yourself this computes 2 to the n. Now, what's gone wrong here? How can we fix this? So we can identify two culprits, and I admit this is sort of one of those things where if you know the answer, then it's easy to see what the culprits are, but I'm going to say these are the culprits in this function. One is that there's duplication of this higher order value f here. And the other thing, which is going to cause problems, is the construction of new numbers. So we've got this successor here, which as we run through the numbers is sort of running wild, generating bigger and bigger and bigger numbers. So both of the implicit systems I'm going to tell you about restrict this use of successor. and also restrict this use of duplication of a higher order value. Because you imagine a higher order value, if we duplicate it, it will do its work twice. And a higher order value, if you're thinking operationally as a closure, it's got some resources it's got embedded inside it. So it's got some of its own fuel which it can provide to its arguments. And if we duplicate the higher order value, we duplicate that fuel that it contains as well. So let's try getting rid of the first one. If we restrict to linearity, then we disallow this bad function here. So we disallow this double use of f because that's not a linear use of f. But we can write the following. We can just write a duplicator for the natural numbers. Because we can still construct them for free, we can write this linear function where I've allowed myself a bit of pattern matching here. But we can take any natural number x and duplicate it by iterating over it and generating the pair of the same value of x. And then we can easily write an add thing, which is a linear function just using iteration. And then we can write multiplication, because at every step of the multiplication, we duplicate the multiplicand, and then we use add. So we can use duplication and multiplication to get add, and then we can do the same thing again, repeating multiplication to get exponentiation again. So if we're allowed to construct natural numbers whenever we like, then just having linearity is not enough. And so, yeah, we get exponential time because we've got to build this thing, takes exponential time, and then we can do it. We can start iterating it as many times as we like. So let's prevent the user then from actually constructing any numbers. So it seems a bit harsh, but let's see where it takes us. So if we're not allowed to construct any new numbers, we can't write duplicate or add or multiply or exponential. And kind of the question arises, can we indeed write anything? So what we're going to do is separate the natural number types into an iterable nat, which is not constructible, but we can iterate upon it. And then we're going to have a kind of non-iterable, this kind of nat with an empty circle. So these are kind of hollow natural numbers. We can build them, and we can do case analysis on them. So here we can pattern match on whether it's zero or successor in this case analysis. But what we can't do is iterate upon them. So we can construct things that we can't iterate, and we can iterate on things we can't construct. So we've got these kind of hollow natural numbers that don't allow iteration. So I will try and, I'll sketch the core of the proof later on that this is actually sound. But to get an idea of why it's sound, the only source of iterable natural numbers is the input. So we can't construct them internally in the program. So if we only allowed this, we would only get linear time in the size of the natural number fuel provided. So because we run through it once, we're linear, so we can't duplicate this natural number. So then we end up just iterating through the size of the input once. So in order to get up to polytime again, we're going to allow duplication of these variables of type nat. And amazingly, this still leads to a system where we're restricted to polytime. So we're not allowed to duplicate variables of higher order type, because that would allow us to get this problem from earlier. But we are allowed to duplicate values of any first order type. So we are allowed to duplicate values of type nat, even though we can iterate on them. And then it's actually easier to prove completeness than it is to prove soundness. But completeness proof that we get all of polynomial time goes like this. Excuse me. Yes, sorry, there's a question. Is the point here to write a language type system which is only possible to write polynomial time functions? Yes, it is. Yes, at this point. And then embed that in a dependently typed language later on. So here, later on, I will sort of sketch the proof that it is possible that all the functions you can write a polynomial time. But just now, to show that we can get polynomial time, let's say we have a step function on tapes of Turing machines, and we have some polynomial with natural number coefficients that we know bounds the runtime of the Turing machine we're going to simulate. And then we can build up nested iterations to get polynomials. So we can write n iterations just by repeating this step function over and over again. We get n squared by nesting them. And even though we've used n twice here, that's okay because we allow duplication of variables of type net. And then we can carry on and get nti iterations for any I we like. And then we can do addition by composition. So that means we can end up with for any polynomial, we can end up with one big function of type tape, lollipop tape, that will iterate the step function that many polynomial times. And maybe it'll overshoot a bit, but that's okay. We can just say the step function recognizes this and just does nothing for the end. So as I said, this system works, but is restricted to everything being driven by NAT iteration. So we get some source of NATs from the input, and then we're told that you can only write programs which iterate upon that natural number. Now, some programs, I would say almost all programs, are more easily expressible by iteration over trees or any other kind of data structure we might take as input. And certainly subbits of programs are more easily expressible by this means. So another system for implicit polynomial time is Martin Hoffman's linear functional programming language, LFPL. And the idea here is the principle of sort of conservation of iterability. So Martin introduced this special type diamond, which you can think of as representing a chunk of iterability. And this is required for construction. So here we are allowed to construct new natural numbers, but we're not allowed to do it for free. We have to pay a diamond every time we construct one. So every time we construct a 0, we have to pay a diamond. So this linear function type here means it consumes our diamond and we get back a NAT. If we want to construct a successor, we have to pay a diamond and give it the predecessor, and it will give us the newly constructed natural number. And we get these diamonds back when we do iteration. So in the base case here, we get the diamond back. In the step case, we get the diamond back. And now notice now I've had to be careful about the context. So there's no shared context in the step case. All we get is the diamond and the value from the rest of the iteration. So we have to pay diamonds to build iterable things, but when we iterate over them, we get the diamonds back. And it's kind of easy to see how this extends to other data types. If we have trees with leaves and branches, then we can pay a diamond to build a leaf, and we can pay a diamond to build a branch or a node. Now, again, I'll show you later on why this is sound. But again, we can see that it's complete. Again, if assume we have a function S that takes us from tapes to tapes, one step of the Turing machine, then we can build up a linear or n choose 1 iteration. So n choose 1 is just n, just by taking in the natural number. And this time we can't duplicate natural numbers in this system, unlike the previous one where we could duplicate natural numbers. We can't do that anymore because if we're allowed unrestricted duplication, we could duplicate our diamonds. And this would duplicate our source of iterability. But if we have a natural number, we can iterate over it and build it up again at the same time. So here in the 0 case, we take our diamond, we return our tape unchanged, but we build up a new 0 with our diamond. In the step case, we take our number and our tape, we apply the step function to the tape, and we build up a new natural number with the diamond we were given and the natural number. So this allows us to take a natural number as input and the input tape and work that many times, but we generate the natural number at the end. And notice here we can't duplicate the number in any way because we have to pay this diamond. We get 1 diamond back from the iteration and we have to pay it to build up the number again. And now to get polynomial time, we have to iterate this idea. So to get n choose 2 iterations, so that's going to be sort of 1 plus 2 plus 3 plus 4 plus 5 plus up to n. What do? Well, in the base case, we do the same 0 trick, but in the step case, we do n iterations for what we've got so far, and then we do another step. So what this is going to do is, in the case where n is 1, it's going to do 1. In the case where n is 2, it's going to do 1 plus 2. Then it's going to be 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. So imagine it's making a gigantic triangle with well, n choose 2 dots in it. And then we can do the same trick again to get n choose 3, just by nesting at this I2 inside an iterator. And then we can do the same trick again to get n choose 4, and so on. And if we iterate this, we can obtain a n choose k iterator for any k. And again, we get the original number back as an output. So then we can chain them all together. And because these binomial coefficients form a basis for the polynomials, any polynomial can be expressed in this form. And so if any polynomial runtime, we can build up enough of these iterators all chained together to get polytime completeness. Okay, so partly these are to show you that these systems are complete, but also give you an idea of how it works to program in them. So in the first system I showed, you have to be careful about duplicating the natural number. You can duplicate the natural numbers and you can use them over and over again. In LFPL, you have to do this kind of diamond trading where you get diamonds back when you iterate, but then you can use them for sub-iterations. Okay. So that was 2 systems for implicit complexity. Let's see another system for explicit complexity. So this is another idea of Martin Hofmann's. This originates with a paper with him and Stefan Jost in 2003, where we take the idea, or they took the idea from LFPL, where diamonds were used to pay for iteration. And we interpret that now literally as a diamond is the cost of a step of iteration. So before, diamonds were some kind of concept of iterability, but they weren't directly consumed. Like there could be n many diamonds in the system, but that didn't mean you were going to do n many steps. Now what we're going to do is reinterpret a diamond as literally the cost of a step of iteration. So the number of diamonds you get as input is directly proportional to the number of steps or number of steps you do, because that's the number of steps of iteration you can do. And this is inspired by Tarjan's amortized complexity analysis. So the idea is that these diamonds are stored within data structure, and they give you, when you examine the data structures, they reveal diamonds to you. And these diamonds are then used to perform computations on those data structures. So in the most basic system, building a NAT still requires you to give some diamonds. So we have to pay for 0 and successor, but iteration no longer gives you them back. So the iterator now just has a base case, you don't get a diamond, and you get a step case, you don't get a diamond. So this means we're back to linear time. So if you get a natural number as input, then it has as many diamonds in it as there are as the size of the natural number, and then you're back to linear time. But we can be a bit more flexible. So what Hofmann and Jost did was they allowed you to annotate the data structure. So I'm just going to use NAT here. They use list in their language, and say that we have a certain number of diamonds per constructor. Now we can duplicate natural numbers as long as we preserve the number of diamonds available. And this means that then when you iterate over it, then you get a certain number of diamonds to use in every step of the iteration. So for example, if you iterate over a list and the list contains 2 diamonds per step, then you can do 2 units of work for every item in the list. And one really nice feature of their system is that you can use linear programming to infer the values for these P's, which allows you to just write things that look a bit like normal functional programs, but you can then infer the resource annotations. So to get back to polynomial time, Hoffman and Hoffman, so now Martin Hoffman and Jan Hoffman, discovered how to adapt this system to polynomial time by annotating the data structures with sequences of naturals. And now the interpretation is that if the natural number is n, then we have this polynomial number of diamonds attached to it. And so you can see this is getting similar to the system, the way that LFPL gets completeness for its system. And then the iterator now gets surprisingly complicated. So they didn't express it like this because they had a system with general recursion. But the way their iterator sort of works is if you take a natural number, which has one diamond for everything in it, plus something else. So this plus one here is what we're going to use to do this iteration. Then inside, we're now doing sort of primitive recursion. So we have access to the natural numbers as we get down. Inside, these have this amount of potential attached to them. And you can sort of work this out by working out what n plus 1 choose I would be here, and then multiplying everything out. And you end up with this kind of additive shift effect here. So we get a slightly different potential for these natural numbers, but remember this natural number is always going to be less than this one. So the totals add up in the end. So we have this plus 1 here to pay for the overall iteration, and then the internal natural numbers have another certain amount of iterability left in them. So this means we can iterate on these ones internally and get back to polynomial time in the same way that we did for LFPL. So this is kind of making all this accountancy explicit in these annotations, unlike in LFPL where you had to do this sort of playing around with rebuilding the natural numbers all the time. But the point of this system, I should make clear, is that the actual time we use is now explicit in the types. So we can read off from the type of the input using this polynomial here, that if we take an input of nat with some annotations, which we can infer using linear programming, then we will know something about the actual runtime of the program. Whereas before, in the other two systems I showed you, they were implicit. We only knew it was polynomial time. So now by counting these diamonds, or the implicit diamonds in the natural number, we can learn something about how many steps of iteration the program is going to use. Okay. So now that was three simply typed systems for controlling complexity. So the first two were implicit, so they're implicit polynomial time systems. And the third one was, you can think of it sort of as an implicit linear time system, but it does make it's explicit in the sense that the complexity is explicit in the types. And this is a sort of more explicit version in that the diamonds are actually in the system of the resource allocated or resource accounted RAML system that Jan Hoffman has been working on. So now, second part of the talk, I'm going to sort of talk about how to adapt these systems to dependent types. And the real challenge here is how to mix dependency with accountancy. So accountancy being how we account for how many times things are used. So remember that in all of these systems I've talked about, linearity of the typing is pretty much essential. So how do we do this? So in Martin-Löf type theory, we have judgments like this. So we have some variables, have some types, and that means that this M has type T. And now the crucial part of this is that these types here, so S or T or any of the types in here, can depend upon variables used earlier in the context. So this is what makes it a dependently typed system. And these variables are mixed usage, by which I mean some of these variables in the context are only here because they're needed to make the types make sense. So they're kind of used logically. But some of the other variables are only there, are actually there because they're used computationally. So if you imagine compiling this program down, some of the variables are not actually needed. They're never used at runtime by the program. They only appear in the types. So here's an example. So let's say we have a context that has n, which is a natural number, and x, which is a finite number, less than n. Sorry, but there's a finite type of numbers less than n, so x is a number less than n. And all this program does is just return x. So this means that we could say x is actually used computationally. I mean, not in a very interesting way here, but the program actually does return x. But the n, we could say, is only used logically or at typing time. So this n is only really used in order to make these types make sense. If we were to try and compile this program to actual machine code, then there'll be absolutely no point in reserving space to store this n anywhere. All it does is take x and return x. The n is only really used to make sure the types make sense. Now, linear logic, by contrast, has a very kind of different reading of what a variable being present or not in the context might mean. So in linear logic, at least in most presentations, the presence of a variable x records its usage. So it says that each xi must be used by m exactly once, or at least once if we're talking about an affine system. So the fact that something even just appears in the context means it is definitely going to be used computationally. And why is this interesting? Well, usually it's interesting because it enables insight into the computational behavior of m. If we know exactly how it uses its variables, if you think of m as being kind of an open system which has kind of ports x1 to xn talking to the rest of the world, then knowing how it uses those ports is of interest. And knowing that it uses each one exactly once is a kind of basic fact to know. And also, as we've seen, we can use this to control the time complexity of how n runs. So let's go back to our other judgment. And now, can we read this judgment linearly? So n does appear in the context, but it's not actually used computationally. So it's not used in the term at all. So is this kind of valid? But it does appear twice in the types. So not only does it not appear in the term, so it's just x in the term, it appears twice in the types. And as I've sort of been trying to say, is it even really used at all? So some systems have tried to integrate dependent types and linear types by separating the logical uses, that's the ones to the left of this bar here, from the computational uses. So we separate the so-called intuitionistic or unrestricted uses. So it's maybe wrong to say these are only logical uses. So this n here could be used in the program, but just in this example isn't. And then we have the linear uses on the right-hand side of the bar. So we separate these intuitionistic uses from the linear uses. And then we're allowed to, well, it depends on the system, but we can maybe use both of them in the term or just the linear ones. And this has got a fundamental restriction, which is that types can depend on intuitionistic data. So this n can appear here because it appears in this context, but we can't use, for instance, x in this type in the conclusion because it's a linear variable. So linear variables can only appear in the programs. So we have this separation between intuitionistic stuff, which can be depended upon, and linear stuff, which cannot be depended upon. And many people have looked at this. So in a simply typed setting, this is due to Andrew Barber with his dual intuitionistic linear logic. And then the dependently typed versions has been several different permutations of different ways of arranging this. So an alternative approach to linearity, or as kind of strict linearity, is to use quantitative annotations. So this is where we mark each member of the context with how many times it's used. So here, for example, as we're saying, x1 is used row 1 many times up to row, and xn is used row n many times. And this tells us a bit more information about how it's used. So linear logic sort of says, yes, it's used exactly once. This might say it's used 5 times, or this might say it's used 0 times. And these row I record usage from some semi-ring R. So semi-rings work well for this because they have just enough structure to say something's being a use. We can say something's not used by using the 0. We can add up uses. So we can take 2 subterms and add up their uses. And we can talk about nested uses by the multiplication. And this has sort of many precedents. So these are some of the older ones. And of course, the granule system that Harley works on is a actual implementation of this kind of system. And by picking different semi-rings, you can get a wide variety of different applications. So we can pick natural numbers to control usage. We can pick sets of principles to get information flow usage, and many other examples. Now, the key point is to try to adapt this idea to dependent types. And our key tool here is the fact that there is a 0. And so Conor McBride's idea is to allow 0 usage data to appear in the types. So in these, if I just go back, in these judgments, if we have something annotated with a 0, then that means it's not used in some sense. That, strictly speaking, depends on exactly what the interpretation of the semi-ring is. But if we say it's not used, that just means we're just going to not use it computationally, but we're still free to use it in the types. So Conor's idea, McBride's idea, is to allow 0 usage data to appear in the types. And this leads to the following kind of system, where we annotate the variables with how they're used, but now we can have dependencies, but the dependencies count as a 0 usage. And now because 0 plus anything is the thing we started with, using things in the types doesn't contribute to their usage, their kind of computational usage. And to get this system to work, we now have to annotate the result with whether or not this thing is going to be used. So we effectively have 2 parallel systems that just happen to have the same syntax almost. One where the sigma at the end is 1. So this is the real computational world. And then we're going to have a sigma equals 0, which is going to be the types world. So you can think about the real computational world. This is where stuff actually costs money to run. This is where there's real memory, there's real resources. We're really going to have to pay for our diamonds to get through and compute things. In the types world, this is what people think academia is like, where we can just run around thinking about things without worrying about money or anything like that. It's all wonderful. And this is just where we can be free in our thoughts and we don't have to pay for anything. I should say that in Conor's original system, you're allowed an arbitrary row here, which makes a very elegant looking system. Unfortunately, substitution is inadmissible in that system. So you have to restrict to 0 or 1 at the end here. And the key point about this system, and the thing that kind of makes it quite subtle, is that we can always go from the real world to the types world. And this is always an admissible rule. So if we've got any judgment which is in the real world, there's a kind of shadow of this real computation in the types world. And this is what allows us to depend upon any program. So this is what gives us full dependent types. So here's that rule again. So if we've got any judgment which is in the real world, so in this 1 world, then there's a corresponding judgment with the syntactically the same term in the types world. So this means that every linear term has a kind of extensional counterpart. So this, well, by extensional, I mean it just has a pure kind of input-output meaning, as I talked about at the start, or it has a constituent extensional part. So this is used at type checking time to construct types. So if, let's say, we write a program here which lives in the real world, then we can use that program in the types because this rule is admissible in the system. This has a rather strong restriction, which has the effect of making the linear system is a restriction of the intuitionistic system. So what this means is that effectively the only properties we can talk about in the linear system are kind of unary properties. So we say that there is some function which is extensional, and then we have some property of that function. But we can't talk about, let's say, binary properties. This is why I hoped when I was coming up with the system that we could talk about binary properties, like as you might see in information flow control or in differential privacy systems, for instance. But it is just enough that it will work with these computational complexity systems, because there we're saying we have a function that takes some gamma to some t, and the restriction in this world is that it's a low complexity function. There's just a question in the chat: does the cost have to be a semi-ring? Is the distributivity strictly required? Yes, it is, and I've even told a small lie here. So in the simply typed systems, we can get away with a semi-ring. Actually, some work that my student James Wood has been doing recently, you can get away with a skew semi-ring. So that's one where associativity only goes in one direction. So you have a partially ordered semi-ring, and associativity only goes in one direction. So you can actually do most of these systems with just a skew semi-ring. But distributivity, I believe, is required. And also for this dependency type system, you have to have a semi-ring which is positive, which means that if you add two things up to 0, then they must have both been 0. And if you multiply two things and get 0, then at least one of them was 0. So that's something I didn't mention here. But yes, you do need distributivity in order to get it to work. Kind of, you can see that here where I've done this kind of 0 multiplication. There's other places where you do a multiplication here, and you want that to distribute all the way through the context. Okay. So now let's try to adapt this to our restricted complexity system. So first we have to pick a suitable semi-ring or ordered semi-ring. So a lot of the examples, and indeed most of the sort of two papers I referred to there by myself and Connor, use this 0, 1 omega or 0, 1 many semi-ring. So the idea here is that either we use something 0 times, we use it once, or we use it omega. And you can think of this omega as like the bang exponential in linear logic. And then you have these operations where if we add anything, we add 0 and 1. Yeah, okay, 0 wasn't a good example for the distributivity. But yes, if you change this to row, then it is different. Yeah, so we add 1 and 1, then we get omega. So anytime we step outside of 1, we just get omega, and anything multiplied by omega that isn't 0 is omega. However, if we allow this semi-ring, then we get an unrestricted bang modality effectively in our system. And this would mean that we wouldn't get polynomial time. So the semi-ring I'm going to use is just the natural numbers ordered backwards for reasons. And the operations are the normal operations on the natural numbers. So this is the semi-ring I'm going to use. Now we can add diamonds to our system. So the type formation rule says that if gamma is a well-formed context, then with absolutely no resources whatsoever, so that 0 is everything in gamma, we can produce a diamond. Sorry, we can say that diamond is a type. And now we have an introduction rule for diamonds, which only works in the 0 fragment. So this is quite important. So in the 0 fragments, as I said, this is where costs don't matter, everything is free. we can just say diamonds exist, and we give this star as the constructor for these diamonds. So in the 0 fragment, diamonds are free. In the 1 fragment, we can't construct diamonds. The only diamonds we can get come from the input. And now to do LFPL, we can construct natural numbers. So to construct a 0, we need a diamond. To construct a successor, we need a diamond. And notice here, these are kind of polymorphic in the fragment of the system you're in. So if this was in the 0 fragment, we could just supply a star for the diamond, and that means we can construct as many natural numbers as we like, because we can just use stars everywhere. Now the eliminator, so this is the dependently typed version of the eliminator I showed you earlier, so it's a little bit complex, but if we have a type A, which depends on a natural number, then in the base case, we get a diamond, which we're allowed to use once. And then we have to construct an A where the X in the A, so A as a free variable X, is a type, we replace by 0. And because we're in the type fragment, we can just use a star for the diamond. This is the types all live in the sigma equals 0 fragment. And in the step case, we get a diamond. We get a natural number that we're not allowed to use. It only exists there for the purposes of the typing. So this natural number is not allowed to be used computationally, but it does allow us to type the A. So we have the property A is true for n, and we have to prove that it's true for a successor of n. So we can use this n in the types, but we're not allowed to use the n to actually write our ms term here. And then we get a natural number, and then we construct the iterator like so. So we then get A is true for all for the n that we give it. And then this plus thing here adds up the two contexts. Okay, and then we can either go on and do other data types, or we can encode some of the data types. So we can define by recursion on natural numbers, the kind of vec data type, by iteration on the natural number. And then we can define lists as pairs of a natural number and a vector of that length. So we can define other data types in this system. To get the amortized analysis system to work, so now we can have a slightly different tactic to the one before. So in the kind of RAML-based system of Jan Hoffman, there the resources are tied to the data types. And this is what gives that system the ability to sort of do effective inference. But now we can separate the two because we've got the power dependent types to talk about the number of diamonds that we need to do anything. So we've got the normal introduction rules for the natural numbers. And now we have a diamond, which is parameterized by this resource annotation as before, which takes a natural number. And in the 0 fragment, we can just use star to introduce these diamonds. So this represents, for any natural number n, we give it as input. This should be on that line below, sorry. This represents that big binomial polynomial I said before of that many diamonds for that natural number. And then we can give the programmer, so rather than the programmer being at the mercy of some inference engine, we can give the programmer ability to do the diamond trading themselves. So they can take a bunch of diamonds and split them up, take a bunch of diamonds, join them together, and shift the diamonds like this. So we've got some diamonds for successor of n, then we get this shift operation to get the diamonds for n. And now for this system, where the explicit diamonds are accounted for, we have this eliminator. So for A depends on a natural number, we have to write the 0 case and the successor case. And to pay for it, we have to give as many diamonds as the size of the natural number we want to iterate on. So this is using the dependent types here. And then all the contexts have to add up. So basically, we have to pay for our iteration as we go. We have to, if we want to iterate over a natural number of size n, then we have to pay with n diamonds. And then to get this nested iteration behavior that the Hoffman and Hoffman system had, then we can do it by making A pass in all the diamonds we need to do it. And then we can explicitly shuffle them around to pay for any nested iterations we want to do. But the point here is that we have to pay with this big D for all the diamonds we want to use up front. So I think now with the remaining time, I'll just quickly go through why this system is sound. So the technique I'm going to use is due to Ugo Darlago and Martin Hoffman again, on generating realizability models for implicit computational complexity. So the way they work is parameterized by what's called a resource monoid. So I've written first here the definition in sort of smug category theory terms, and I'll give you a better definition in a second. But let's say that just let n minus infinity be the category with objects that are all the natural numbers along with a minus infinity, and an arrow from m to n if m is less than n, where minus infinity is less than everything. So this is a strict symmetric monoidal category with plus. And then the kind of annoyingly terse category theory definition is a resource monoid is a n and minus infinity enriched strict symmetric monoidal category. So what does this mean? This means that we have a commutative monoid, M, so that's the strict symmetric monoidal bit, such that there's a kind of difference operator between every two elements of M. So this kind of Hom object here says that this is sort of the difference between the first and second argument. I've written these in the wrong order. So M of alpha beta is the difference between alpha and beta. And the idea is that the elements of M are going to represent amounts of potential in our data. And then when we do a computation, we're going to start with some potential alpha, do something, and end up with potential beta. And the difference between those two will be the number of steps of computation we have available. So we consume some of the input by doing some computation, and then we have some potential left in the output. And then these have to satisfy these equations. So the difference between alpha and alpha can't be anything less than 0. And we have this kind of inverse triangular law that going from alpha to beta and beta to gamma is less than going from alpha to gamma. And this is the symmetric monoidal part as well. So some examples, the simplest example is just the natural numbers, where we just take the difference, but only if n is less than m. Otherwise, we get minus infinity. So this is not going to count the number of steps, but just the number of recursion steps. So this is the monoid we want to use when we're just counting our diamonds in the explicit system. For the LFPL system, we're going to use this one, where we use pairs of a natural number and a polynomial with natural number coefficients. So what does this mean? Well, we can think of each of these components as everything in our system has kind of two aspects. It's got a kind of passive weight, which is the number of diamonds in it, which is the natural number. So this natural number here is going to record the number of diamonds, which is in some data. And the polynomial is a kind of active weight. This is if I'm an object which is applied to something which has m diamonds, then I have enough potential to do p of m steps. So this is what we use to do higher order things. And then we just add them to get for the monoid operation. And the differencing is done by taking the bigger number of diamonds and taking the difference between the two polynomials. So the polynomial I have left at the end is p, actually works backwards. And then, crucially, well, interestingly, the constructor-free system works by, instead of when we add two of these things together, we take the maximum of the number of diamonds in them. And we'll see why that is in just a second. But otherwise, everything else is the same. And originally, Dalago and Hoffman used this resource monoid for Lafont's soft linear logic, if you know what that is. And then to get this to work, we have to assume a model of computation that has a cost model. So I use a big step operational semantics. So we take expressions E with environments eta, and then in k steps, we reduce to some or compute to some value V. And then to construct a model of the calculus, I won't go into all the details, but let's just say that types are interpreted as a pair of a set and a realizability relation. So X is kind of the extensional content of the type. This is the set of values that the type contains. And the realizability relation says that for this resource and this value in our operational semantics, realize this, this actual extensional value. And then a function from X to Y is an extensional function. So this is what I was saying about everything has a extensional constituent, such that there exists an expression which interprets it and an amount of potential that goes with it. So this is kind of its inherent potential, if you like, in the function, such that for any value we give, which has potential alpha, there exists a final potential beta, and then right down at the bottom here, the number of steps taken is the difference between the input potential and the potential of the function and the potential of the output. So this is how we can sort of work out that everything's accounted for within the system. And this is my sort of second last slide, but just to give you an idea of how this works. So in the amortized system, diamonds, we pay for them by saying, well, we must have at least as many things, things in our resource monoid to pay for the diamond. So must have greater than one or greater than or equal to one resource to pay for having a diamond. In LFPL, we have the same thing, except we also have this polynomial, which must be greater than 0. But the natural numbers, the resource we require in here, in this n, must be greater than the actual size of the natural number we want. And the same in the constructor-free system. But you can see in the constructor-free system that when we add these resources, we're taking the maximum. And this is what allows us our ability to do duplication. Okay, and so that was everything. So we're a bit technical there. So what I've tried to show you is this quantitative type theory, which I've been working on for a few years now, works for complexity analysis. So we can take the implicit computational complexity systems that were simply typed or polymorphically typed before and make them dependently typed. And this uses a careful combination of dependency and linearity. And we can still use dependent types for reasoning about programs, but now we can use them for reasoning about complexity, at least especially in the explicitly typed system. So there's some related work, which I haven't covered, so it'll be size types, but people have used this for complexity analysis. So Niels Anders Danielson has done this with these kind of tick monads, where you have to annotate your program with a little ticking thing, which counts up how many steps you use. And Marco Gabardi and Ilgo Dalago have this linear dependent types for implicit computational complexity, but there the dependent types are not full dependent types. They only allow you to talk about natural numbers for counting the time complexity. And in the future, well, the main thing I want to do is to implement this system so I can actually give you some examples rather than the kind of small examples I've written so far. But there are many more implicit computational complexity systems like light affine logic, elementary affine linear logic, bounded linear logic, systems for log space, that kind of thing. And I think one interesting thing is to look in a type theory version of polytime mathematics. So model theorists and other logicians have looked into what's kind of polytime Heyting arithmetic and things like that, but now we can do polytime type theory. What is the kind of things where if we restrict to the proofs being polytime, what kind of interesting things do we get? Okay, thank you very much. That's everything I have. Thank you for coming.
Thanks. Yeah, that was awesome. Does anyone have any questions? We have a little bit of time left, I think. Well, we're right on 2, but some quick questions. Maybe Bob won't mind answering them.
So the question there from Mikhail. So assuming we have an arbitrary monoid for some esoteric resource, can we just construct these resource monoids with some standard construction? I'm not sure. So this difference operation is quite subtle in that to get it to work. So this point here about the this counting the recursion steps and not the actual number of steps. So what I wanted it to do was have a system where, so here we have, in this system, we have a number which counts the number of diamonds and a polynomial. And I was hoping to get a system to do linear time by just restricting this to be a linear function. And this just doesn't work. Like the main problem is you just can't get this, well, doesn't work. You end up with a kind of pushing down the carpet in one corner, it pops up somewhere else sort of problem. You end up with either this triangle inequality, backwards triangle inequality doesn't work, or you end up with the iterator doesn't work in some way. So I don't know of any kind of standard way of taking an arbitrary monoid and getting one of these resource monoids in a way that's useful to make a system. I think you could do it in general if you didn't care about getting an iterator to come
out. Yeah, so Bob, there's a question on YouTube from Spites, maybe? Sorry if I'm most likely pronouncing the name incorrectly. Is there any use in considering the cost of forming a type, i.e. keeping track of the resources you need to ensure a type is well formed, even if getting types depending on linear terms is tricky?
I think there is. There's certainly reasons for it. There's 2 reasons I can think of. One is that sorry, Andre's just asked me to show the linear. I realize we do stuff again. One reason is that, well, I said that we don't care about the type stuff because it doesn't happen. But of course, when I'm using Agda, I hardly ever run the programs and I type check them loads of times. And I'd like that to run efficiently. So that's one reason to want that. Another reason, I think, is people would say that one sort of characteristic feature of intentional type theory is that you don't have to have any kind of external source of evidence to prove that this really is a proof. You can just type check it. However, that type checking may not finish before the end of the universe, right? So this is a kind of empty promise in some sense. You can't use this as your kind of without a timeout. You can't use this as your gold standard of evidence. However, one could imagine this polynomial time system working at the type level. I think this would be a really interesting thing to make work. And then somehow, there's quite a big gap here, getting a system where all type checking must be polynomial. So you're not allowed to do anything which has unrestricted complexity in the types. And I believe that our host has a paper at Popple this year, which has a system which might be able to do that.
That one was with Stephanie and Pritom as well. I don't know if Rich is here or not, but the one at Popple doesn't have the type level stuff in it. But my paper being reviewed at ESOP does.
Okay.
Somebody's there we go. Yeah, that was a great question. Does anybody else have any last questions?
So Andre asks on the Zoom chat, how rich a structure of dependent types do you get? Products, sums, universes. You get everything and more because you get linear versions of them. So you get products and you get tensor products. So you get sigmas and you get sort of tensor sigmas, and you get universes as well. Yeah. So the key thing that makes this work is this this zeroing aspect here, which means basically, well, it's not quite this, but the zero system is basically just Martin-Löf type theory.
Yeah.
So you can have anything you like in there, you can talk about them, and then you can restrict the one fragment as much as you like. So in the Licks paper where I sort of talk about this, they're the same, but in the types fragment, the tensor products just become normal products. But you could restrict the one fragment so it was very, very restricted. So one thing I'm interested in doing is restricting it so you can only write reversible programs, for instance. And there you might not even be able to construct sort of just products at all. Oh, sorry, you might not be able to construct sums.
There's a couple questions before Frederick's on YouTube. There's one that says, can a system prove better complexity bounds than RAML, such as logarithmic bounds?
Not at the moment. So you can prove tighter bounds because you have to do the work yourself using the split, join, and shift things. And so you have to explicitly divide up the diamonds yourself, but you can't get logarithmic bounds. These seem to be quite hard to get with a system which sort of just works by iteration, because a lot of the time you have to do something like divide a number by 2 and then account for the fact. So I mean, this is why I say about I need an implementation. I want to experiment with this system and actually program with it. So it might be possible to do the right amount of diamond shuffling that you could get logarithmic bounds. But it's sort of, it's a bit like RAML, except you have to do the accounting yourself. It isn't an inference system. On the upside, you don't have to hope the inference system does it for you. You can do it yourself.
Another question was, I think it's Matthias. I didn't get the remark about Connor's system being able to deal only with unary things, predicates. Could you explain that a bit or point to some literature on
that? So only being unary properties.
Right, yeah.
So this is a kind of subtle property. It arises because, so let's say this M here in this term here had kind of, we wanted like 2 interpretations. If you imagine kind of doing binary logical relations with it. So let's say you're proving some kind of information flow property and you want to say, okay, there's 2 interpretations and they can't distinguish between these 2 inputs or something. So a binary logical relation. But then if you think about how this is interpreted semantically, the admissibility of this rule, it says we take one of these interpretations and project it. And if you've got 2, then it just doesn't work out. I mean, I've tried over and over again different ways of rearranging stuff, and it just doesn't work out. And you end up, because you've got 2 types which depend on 2 different values, you can't get one single type that it depends on at the end. Right. So I think this is one of the challenges, is to try and adapt this system so that it would work for something like information flow types or differential privacy or something like that.
Great, thanks. That's it from YouTube. So Frederick is up next.
Okay, so the question is, to what degree can actual bounds be inferred or determined? We write types of functions with runtime, linear, quadratic, and so on. Yes, so with the system with the diamonds, the explicit diamonds, then as you can see here, it sort of takes in as many diamonds as it needs to do this iteration. So the type of the overall function will be, here's my input, and then depending on my input, depending on the size of the input, these are the amount of diamonds I need. So the type will tell you that that function has or consumes this many diamonds, and so that tells you that's going to be an upper bound on its runtime.
Cool. Okay, so I think that's it. Thanks a lot again, Bob. This is a fantastic talk. I've learned a lot about various things here, so thank you.
Okay, thank you. Thank you very much for inviting me, and I hope to actually come come visit you sometime.
Yes, yeah. Don't worry. As soon as this pandemic is over, I'm definitely going to have you come down. So for sure.
Okay, I'll just stop sharing then. Okay.
Yeah, great. Yeah, feel free to take off. I usually hang out until everyone leaves just to make sure students don't need me or something. But yeah, that was great.
Hey, I just wanted to say hi in person. Hi.
Hey, how's it going?
I got to run. Bye.
Hi.
Bye.
Okay, I feel kind of weird. I haven't left like 10-mile radius of my house in the last 10 months.
Yeah, I don't doubt it. I've left a lot more than that, but not too much. I try to stay home as much as possible.
Yeah.
But do you all have like restrictions where you can't go more than that, or is that just because you want to remain safe?
It's probably remain safe. I don't actually drive, so we're going to cycle. So to go any further, I need to take the train or a bus or something. So
yeah, that's nice.
Yeah,
so that wouldn't be
yeah,
advisable, right?
But I mean, at the moment, half of Scotland is